Okay, we are moving on to part 2 of this video series. In part 2, we are going to start talking about protein-mediated diffusion. I'll hopefully be able to explain this out pretty well with a little chart here. So off of protein-mediated diffusion, a couple branches here. Start off with passive diffusion on one side, and on the other side we have active diffusion. And so the difference between these two types of diffusion is on the left side with passive diffusion, it only really requires kinetic energy. On the right side, it is going to need a little bit more than kinetic energy to help this diffusion along. And then branching off of passive diffusion, we have two types here. We're going to have simple diffusion and facilitated diffusion. And so the difference here is basically simple diffusion occurs really just off of concentrations. So as the concentration within or let's say on the outside of a cell of a specific ion is higher and inside the cell gets lower, it will just allow diffusion directly through the membrane to even out those ions. And so off of a little chart here, we would put rate on the y-axis and concentration on the x-axis. It is completely dependent on concentration here. The rate will be completely dependent on concentration. So the higher the concentration, the faster the rate will be. And there's a little equation, but we're not going to worry about that right now. So comparatively, for facilitated diffusion, it's going to require help from specific proteins. So we're going to have a few different types of proteins here. We'll have mechanically gated proteins. We'll have chemically gated proteins. And we will have voltage gated proteins. And then we'll have pore proteins as well, but those are just kind of always open, similar to simple diffusion. And within each one of these, they require a specific type of input to allow these proteins to open to allow the flow of ions. And so with mechanical, it's more of a outside force of, like, say, pressure on the skin could allow the open of a mechanical facilitated mechanically gated protein. But for chemically, let's say a certain protein comes along and it would allow it to open. Or for voltage, it requires a certain amount of electricity or volts to open it. But for these ones, with this chart here, we have the rate again as the y-axis and concentration as the x-axis. The difference here is it will initially be very similar to simple diffusion, but it will level out as it reaches its max concentration, because you only have so many of these proteins on the surface of the cell. And as those are saturated, they can only take in so many at one time, which levels out the rate. So it'll be, if all of them are saturated, taking in whatever they're planning on taking in, it will have to level out there. And then moving on to active transport here. Here, I'll change that to transport. Active transport. We have a couple types here, but active transport specifically requires energy mostly in the form of ATP or GTP. And this will always have a molecule going against its gradient. So at least one molecule going against gradient, meaning it will be working towards the higher concentration of either inside or outside the cell. And we have another two types of here. We have primary active transport and secondary active transport. And so within these, primary active transport directly uses ATP and only pumps against gradient. A prime example of this would be like the sodium-potassium pump. And so it would, let's say you have a cell, you have your sodium, which is inside the cell, you have potassium, which is outside the cell, in this case, and then we'll have this pump here. And then specifically for sodium, potassium, you would be pumping. Here we have a higher concentration of sodium outside the cell and a higher concentration of potassium inside the cell. But to continue keeping this gradient high, we would be pumping 3 sodium ions out against its gradient to the higher concentration on the outside, and we'd be pumping 2 potassium into the cell against this gradient again to the higher concentration of potassium within the cell. And so that's going to require ATP being turned into ADP to allow that to happen. For secondary active transport, it will indirectly use ATP. And so it does this by using this gradient that we created over here. And since this uses ATP, it will, to make the gradient, we indirectly use it with secondary. And so we have two types again here. We have symport and antiport. And so with symport, let's say we have a high concentration on this side of sodium and a low concentration on this side of sodium. And this is the membrane. And this is the protein here in the middle. And then on the outside, whatever we're trying to transfer has a low concentration. Inside there is a higher concentration. And so symport, we'd be transferring from the high to low of the sodium, which is using, like we said, that concentration gradient, to then carry in as well what we want inside the cell, carrying against its gradient. For antiport, it's very similar, but we have the high concentration again on the outside, low concentration on the inside, but then we have high of whatever we're trying to bring in on the outside, and we have, or this time it's high on the outside and low on the inside. And so antiport, they'd be going opposite directions. So it takes a sodium in, and then because of that, it pushes the molecule we want to push out. So it's opposite. So symport, it's together, antiport, it's against. And so that is secondary there for symport and antiport. And moving on, we are going to talk finally about osmosis real quick. And so osmosis is specifically talking about the movement of water and is against certain permeable membranes. And so when we have a high concentration of a specific solute and a low concentration on the other side, and we have water levels here, the water is going to shift to try to balance out the osmolarity. And so the water is going to want to shift towards a higher concentration to try to balance out. And so osmolarity specifically would be particles in a solution, so osmoles per liter. And that's different from moles per liter, because moles per liter specifically measures the concentration of a specific type of molecule, while osmoles takes into account all of the solutes within a solution. And so, like, a good example of this would be, you have NaCl. Moles would only take into account it as NaCl, as osmoles would take into account as it dissociates as Na and Cl. So you'd have two different molecules within there, and osmoles will take that into account. And so from there, the difference between osmolarity and tonicity. So we have osmolarity again, and this is just looking at it's focusing on just the measures of solutes. So let's say it's separate. We have a cell at a certain concentration. Within a cell, it's usually around 300 milliosmoles per liter. And within a solution, we can be, let's say it's 300 as well. And so what we're doing with osmolarity is just comparing the two. So in this case, they're equal. So we have a couple different descriptive words. We'll have iso, hypo, and hyper. In this case, iso would be same. And then in a different case, we'd have hypo, which would be less than. In this case, we'd have to specify what we're comparing here. And so let's say within the solution, it becomes 600 milliosmoles, and the cell stays at 300. And so the solution would be hyperosmotic compared to the cell, but the cell would be hypoosmotic compared to the solution. And then when we talk about tonicity, it's when we combine the two. So now we have the cell within, it's at 300, and depending on what the solution consists of, it can change. It could be absorbed into the cell. So let's say if we had urea, we put 300 milligrams of urea into the cell, and the cell consists of 300 milligrams of sodium. Then 150 would go into the cell from the urea, which would then end up with a cell that has a concentration of 450 within the cell, total milliosmoles, and outside of the cell would be 150. And so in this case, beforehand, the osmolarity of the cell and solution would have been isoosmotic, but now the cell compared to the solution is hypertonic, or the solution compared to the cell is hypotonic. And now there would be a transition of water into the cell to balance out that osmolarity. And that is the basic difference between osmolarity and tonicity.